So there's a ball and it's rolling and it's released down a frictionless slope. So here we don't have to consider friction at all. There it comes. And then they say that 5 meters above a horizontal surface as shown in the diagram. But there you can see that it eventually lands up on a rough slope. So there we're going to consider friction. As it reaches the bottom of the slope, the 3 kilogram ball maintains a constant speed. Okay, because remember there will be no opposing forces, so it will stay going at a constant speed until it reaches the rough surface with a coefficient of kinetic friction of 0,3. First, you've got to state Newton's second law, and again, I'm going to stress how important it is that you learn your laws. So, if an unbalanced force acts on a body, you can look this up, the body will accelerate. That acceleration will be directly proportional to the force and inversely proportional to the mass of the body. Now they want you to sketch a fully labeled free body diagram. Remember, for free body diagrams, you need to point the arrows away from the body. The first one is a force called weight. The second one is the resistance of the surface against weight, so that those two are in equilibrium. And it is while it is moving on the rough surface, so it will be suffering under friction. So friction will be working against the motion, so you will call that a frictional force. Remember, friction is actually a concept. It's a theory. It is a little bit like gravity. You get a gravitational force and you get a frictional force. Friction and gravity are not forces and cannot go onto the diagram. Then it says calculate the average frictional force acting on the 3 kilogram ball while it is traveling on the rough surface, and we know that the frictional force is equal to the coefficient of kinetic friction, mass, gravitational acceleration, so we've got 0,3. We've been given the mass, 3 kilograms. We know gravitational acceleration. Remember that this is actually equivalent to the normal. Why? Because the weight is mass times gravitational acceleration and is equal to the normal. And I get 8,82 newtons. The first chimpanzee to be launched into space was named Ham. He was born in 1956 and sent into space in 1961. Ham was sent 753 kilometers above the surface of the Earth before he returned to Earth. Ham had a mass of 40 kilograms. State Newton's universal law of gravitation. Now remember, again, this is a piece of theory. We're now up to about 10 marks that you would have lost if you didn't bother learning your theory. You've got to learn your theory. Any two objects in the universe attract one another with a force that is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. So we've got F is equal to G m1 m2 over r squared. That's what it boils down to. And remember, when you can see that, you don't even have to learn your law off by heart, because you can say any two objects in the universe, and they're two objects because they're two masses, attract each other with a force. That force is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. Calculate the magnitude of the gravitational force acting on Ham when he was 753 kilometers above the Earth's surface. Remember to convert the kilometers into meters. They're not going to tell you that in a matric exam. And the distance between Ham and the center of the Earth and the radius of the Earth is 6,371 kilometers, and the mass of the Earth is 6 times 10 to the power of 24 kilograms. So let's do our substitution. We've got the equation already up there. G is 6,67 times 10 to the negative 11. That's on your information sheet. The mass of the Earth, 6 times 10 to the 24. The mass of Ham, 40. Then you're going to take the radius of the Earth, which is 6,371, plus how far above the Earth that Ham was. That's the total distance between them. It's all in kilometers. I need it all to be in meters, so I'm going to multiply it all by 1,000. And then don't forget to square that. And you land up with 315,42 newtons. Ham weighs 392 newtons on Earth, which is fine because it's 40 times 9,8, so that's not a big surprise. How much would he weigh on a planet with twice the mass of Earth and 3 times the radius of Earth? So all you need to do, I mean, I suppose if you wanted to, you could say, what's 40 kilograms? And then you could double up and give 3 times the radius of the Earth. And then you could use, what was it, twice the mass of the Earth. And you would land up with a whole bunch of information. So, or you could just be clever and easily change it to saying that I'm going to double that mass, 2 times the mass, and I'm going to have 3 times the radius squared, which means I'm going to have a 9 on the old force. So I take 315,42, and instead of it being r squared, it is now 9r squared, so divide by 9, and take this number because of the fact that it's double the mass and times by 2, and I land up with 87,11 newtons.